Okay, so today's topic for Math 12, class number 8, will be the topic of uncertainty. What does uncertainty have to do with math, and particularly with measurement? It is simply this. It is impossible to obtain an exact measurement from any measurement device. Any measurement device. Therefore, there's always a certain amount of uncertainty when we are measuring. And we do this by, we take the measurement value, whatever that is, 50 millimeters or 20 centimeters or 2 meters, whatever it is, plus or minus the plus and minus the uncertainty, by what degree it might be out. Let's look at an example to give you an idea of how this works at the top of page 28. So go to page 28 in the package. If you look here, figure A is a 5 centimeter ruler, also broken up into millimeters, and then figure B, something similar. Figure B is inches broken up into parts. What is it, 1/8 of an inch here? 1, 2, 3, 4, 1/10 of an inch. Anyway, if we look here, this line is a little bit less than 1. So we could say that this line is at 0.95, little less than 1, plus or minus 1/100th of a centimeter, 0.05, 5/100ths of a centimeter, not 100, but 5/100ths of a centimeter. It could be less, could be out by less than 5/100ths of a centimeter or more than 5/100ths of a centimeter. We're talking about a very small amount. That's between 0.95 and 100, okay, or 1. Hold. The second one here, again, very similar. It's at about approximately 0.95. In figure B, same idea. 0.05 or 5 or out by about 5/100ths. Okay, so there's always a bit of an amount of uncertainty in any kind of a measurement. So, further to that, the uncertainty, more information here. The uncertainty of a measurement device is determined by the smallest scale. The smallest scale on a measuring device. So you take your smallest scale, and then what is the uncertainty there? What are the measurements that are not quite exact? The smaller you go, the more precise it will be, and the less uncertainty there is, which of course is millimeters. But even with millimeters, there is a small degree of uncertainty. So let's talk a little bit about uncertainty on pages 29 and 30. There's several examples that we're going to read through and clarify. Beginning on page 29 with example 2. Leela measures the radius of a circle and finds the radius to be 28 millimeters. State the precision of the measuring device used. It's to the nearest millimeter. State the uncertainty. It's plus or minus half a millimeter. So she could be out by half a millimeter, which of course isn't much. It all depends how fussy you want to be. So she should report that she found a measurement that's 28 millimeters plus or minus 0.5 millimeters. That's how she should record that if she's recording the uncertainty. Now, of course, when it comes to uncertainty, you're using it to measure things that have to be very, very precise. Example 3. Brandon measures his height and finds it to be 72 centimeters. The precision of his measuring device is accurate to the nearest centimeter. What's the uncertainty of the measurement? It can be within 5/100ths of a centimeter. And he should report his height as 72 centimeters plus or minus 5/100ths or 0.05 of a centimeter. So you can go with smaller, like a millimeter. You can't really go much beyond half because it's so small, but a centimeter, you can go down to hundredths of a centimeter. Like a millimeter is 1/10 of a centimeter. Therefore, you can go down to hundredths of a centimeter because you can cut a millimeter in half again. Hope you get the idea of that. So a half or a tenth versus a hundredth. Okay, you can always go. Like there's 100, it's all about the idea of there's 10 millimeters in a centimeter. So plus or minus 0.5 millimeters, half of a millimeter, versus plus or minus 5/100ths of a centimeter. Well, there's 100 centimeters in a meter. So it's all your uncertainty is based upon those things. If we go back, the uncertainty of a measurement is determined by the smallest scale on a measuring device. Centimeters are hundredths, meters are tenths, and so we always take half of whatever the smallest scale is. So we always use the 5, we're always using the 0.5, then we just need to decide if it's tenths or hundredths or thousands, and that all depends. Like there's 10 millimeters in a centimeter, we use tenths. There's 100 centimeters in a meter, we use hundredths. The true measurement of an object cannot be absolutely determined because of the uncertainty of measuring devices. Devices with greater precision may provide increasingly precise answers. However, these answers aren't necessarily accurate. In some situations, a reference value is accepted as the true value. For example, we use 3.14 as a value for pi. Even though 3.14 has a beastly long decimal, we use 3.14 as the accepted value. We accept that when we're measuring circles, it's never going to be completely accurate. We just accept that when we're measuring the circumference. This value isn't truly accurate, but it is the accepted value, as it says. It gives, in other words, most of the accepted value will give us what we need to get the job done. Same thing with millimeters. We know that millimeters aren't completely accurate, but they're as accurate as they need to be to get the job done. For an instrument to provide accurate readings, it must be calibrated. To calibrate means to adjust or make corrections. Therefore, instruments may need to be adjusted in order for them to provide accurate readings. Consider the following example. So flipping over to page 30. Okay, I thought I'd done 1 and 3. Yeah, let's do example number 4 on page 30. A 100-gram baseball. So it actually weighs 100 grams, is weighed 3 times on a very precise scale. The weights are 84.253, 84.258, and 84.531. Comment on the degree of precision of the scale. It says the precision is good since these measures are all very close. They're all within 100th of a gram, 523, 528. So these are within 500ths of a gram of each other. And then 531, this is within 300ths of a gram of this one, and this is within 800ths of a gram of this one. Okay, so very, very close to each other. What's the degree of accuracy? The accuracy is out to lunch. The baseball is supposed to be about 100 grams, and it's only showing up as 84 point something. Okay, and of course, what might cause the measurements to be inaccurate? The scale needs to be calibrated. Maybe there's an error. Maybe they put the wrong baseball on the scale. That's possible. Or if it were heavier, maybe someone had their hand on the scale as well. So human error, the scale needs to be calibrated, and so different possibilities as to what could cause the error. It's time for some brain power, and then we're going to look at some more exercises on this. You will be getting your next hand-in assignment today. But first, brain power on page 31. Let's read the exercises first. If a volume of 2 by 2 by 2 cube is 8 units, approximately how many times larger would the volume be if the dimensions of the cube were 5 by 5 by 5? 135 centimeters is how many meters? Simplify the fraction. 3 feet, 1,212 inches is how many feet? Consider the expression y equals 3x. What is the value of y, of x, when y equals 54? So, some relatively simple mathematics. A 2 by 2 by 2, 2 times 2 times 2 is 8. 5 times 5 times 5, done without a calculator. 5 times 5 is 25. 25 times 5 is 125. How many times bigger than this is this? 125 divided by 8. Okay, let's try and do this with a little mental math. 8 times 10 is 80. 11 times 8 is 88. 12 times 8 is 96. Let's keep going. 20 times 8, that's too big. That's 160. So then we're going to go less. Let's try 15 times 8. 10 times 8 and 5 times 8 is 80 and 40, right? Is 120. So we can say 15 times 8 is 120. So 125 divided by 8 would be 120 point something. We'll need a calculator to get the exact answer. Sorry, I mean 15. I meant 15 because it's divided by 8 is 15. 15.625 times bigger. So about 15 times bigger. $135 centimeters. Well, there's 100 centimeters in a meter, so 1.35 meters. 3. Simplify the fraction. What can I divide both of these by? By 2 for sure, but I'm sure I can do better. I can do 10. 40 divided by 10 is 4. 300 divided by 10 is 30. You cannot divide both of these by the same number, so it's 4 over 30. 3 feet and 1,212 inches. Feet, inches. So we got to get that 2,212 into inches. There's 12 inches in a foot. So 1,212, 12 inches in a foot, divide by 12, 101. And that simply then becomes 101, add 3. This becomes 104 feet. 5. Y equals 3x. What happens when y equals 54? That's y this time. Y equals 54. So put 54 in for y equals 54 equals 3x. 3 times x equals 54. 3 times a number is 54. How can we find out what that number is? Guess and check. You can do 54 divided by 3. Like this with long division. 3 times 1 goes in once, 3. 5 take away 3 is 2, 24. 3 into 24 goes 8 times. So, what is the value of x when y equals 54? Therefore, x equals 18. 3 times 18 equals 54. Let's put a little therefore symbol in here to pretend we know something. All right, I want to look at examples 1 and 2 on page 32. So flip over to page 32. And we're going to do those exercises together. It says, describe the precision of the measuring device used and the uncertainty of the following measurements. Okay. So, page 32, number 1. Got a fresh page because we're going to run out of space here anyhow. Page 32, number 1, 54.3 millimeters. Now we're going to go with some shortcuts. We're going to go M for measurement and U for uncertainty. So measurement is 54.3, nearest 0.1 or nearest tenth of a millimeter, mm, and UC, uncertainty, for millimeters, it's within the nearest 0.1 of a millimeter. So we will go half of that. We will go to the next. We'll divide the tenth by a half. It'll be plus or minus 0.05. So it's 100th. So this measurement in millimeters was given in tenths. They obviously used something like a micrometer or micrometer or a caliper that can go less than 1 meter. And so you could get tenths of a millimeter. So then your uncertainty becomes hundredths of a millimeter. So 0.05. And the 5 is the number that you always use for uncertainty. So that's A. B, 48 meters. Okay. Measurement. Precise to the nearest meter. Don't have any decimals here. To the nearest meter. Und UC, uncertainty. So if we're going to be precise to the nearest meter, then we're just going to take a meter. We're talking about a whole meter. And we're going to use the 5 again. So we can go to tenths of a meter. 0.5. It's precise to the whole meter, so it's precise to the nearest half of a meter. Okay? Does that make sense? You're dealing with a whole meter, so then you take half, no decimals here. You're dealing just with the whole number, so it's precise to the nearest half meter. 0.5 of a meter. See? 46.4 centimeters. Now, 0.4 of a centimeter, that's millimeters, right? So this means that this is basically 464 centimeters, or sorry, millimeters. So let's say, we'll convert this to millimeters, because if once you're dealing with 0.4 of a centimeter, you're dealing with millimeters. So this is 464 millimeters. So you've got your measurement to the nearest millimeter. I was doing a recording here. No worries. I'm not talking, well, I sort of am talking to myself. So your measurement is to the nearest millimeter in this case, and the uncertainty then is the nearest 0.5 of a millimeter. You're dealing with a whole millimeter, not a decimal of a millimeter, so 0.5 millimeters. So always, whatever the closest precise measurement is, you take half of that measurement. I hope that's beginning to become clear. If we'd stayed with centimeters, we could have used 0.1 of a centimeter here, right? A tenth of a centimeter, then it would be 0.05 centimeters. That would also be correct. But we use the millimeters. D. Now we're dealing with 10 thousandths of a millimeter. 35.733 millimeters. This measurement is precise to the nearest 10,000 of a millimeter. No, 100,000 of a millimeter, right? Because 4 zeros would be 10,000. To the nearest 1/100,000 of a millimeter. That's incredibly precise. That would be microscopic. And then, what's half of this? What's half of 0.00001? Well, you're just going to add another 0 and a 5. Here, show you. Do a bit of a demo here. I'll put it on the screen once I've got it right. It did it in scientific notation, so that's not helpful. But anyways, you take this number and divide by 2, and you get your uncertainty, which would be plus. I should have done plus or minus up here. Forgot. The uncertainty is plus or minus point. And you're going to have 5 zeros, 0, 0, 0, 0, and a 5. You always have the 5. 0.000005 is your uncertainty. So let's just say there's not a heck of a lot of uncertainty with this measurement. E. 2362.24 centimeters. Measurement equals 0.24. You could go with millimeters here, I guess, but that would be a massive number. Let's just say it's precise to the nearest. We've got 2 decimal places. Nearest 0.01 of a centimeter, because you got 2 numbers after the decimal. And your uncertainty uncertainty in this case. 0.01, you add another 0, 0.005. Half of this with the zeros, add the 5. It's always half, always, always, always. Okay, let's look at example number 2. Frederick measures the radius of a circle and finds the radius to be 35.75 millimeters. What's the precision of the measuring device? What's the uncertainty? And what measurement should he report, including the uncertainty? So, that's number 2A. So he's got a radius of 35.75 millimeters. What's the precision of the measuring device? P equals precision 0.75 of a millimeter, so it's the nearest hundredth, 0.01 millimeters. B, state the uncertainty of the measuring device. Just tack on another 0, plus or minus 0.00, because there's 2. There's 1 0, stick on another one, and the 5. 0.005 millimeters. How should he report this measurement? If he's including the uncertainty, 35.75 millimeters plus or minus 0.005 millimeters. Okay. I moved this too fast. I'll pause a bit here. Talk about our next Hendon assignment. It goes from, and I'm scrapping one of the questions on it. Just be aware of that. So the assignment is called accuracy, precision, and uncertainty. You will find it on pages 33 to 37. We're doing questions 1 to 7. We're skipping question 8, and it will be worth 27 marks. Accuracy, precision, and uncertainty, pages 33 to 37, numbers 1 to 7, 27 marks. There it is. Cross out the 29, replace it with the 27. Here you see question number 1, where you compare accuracy and precision, or both or neither. Very similar to the one activity with the targets a few pages back from class number 7. Here we have the length of the string precise to the nearest indicated unit using the given imperial unit. So 1/8 of an inch, 1 inch, half inch, quarter inch. Every single time, how close is it? Three. She measures the dimensions of the painting. How precise are the measurements? They're precise to the nearest 1/10 of a centimeter, or 0.1 of a centimeter, right? Then you find the perimeter and the area. Perimeter is adding your sides together. Area is simply length times width. Explain how accuracy is related to uncertainty. Let me give you a page number for that. That's bottom of page 29. You give they use the example of the measuring a circle. you can certainly use that information to answer this question. It's there for you to use. It's fine. Describe the precision of the measuring device and the uncertainty of the following measurements. Let's do one. Let's do the first one. So this is precise to the nearest centimeter. So we're talking about a whole centimeter in this case. There are no decimals. So uncertainty plus or minus 0.5. If you're talking about a whole number, you take the whole number, divide it, you get 0.5. 0.5. Right? Here you have 0.6. So it's already a decimal, so 0.05 of a millimeter will be your uncertainty. Here again, this will be 0.5 of a meter. Here you're going to add another decimal point, 0.0005 of a centimeter. Okay? I hope those precision things are clear for you. She measures the diameter of her pencil eraser and finds it to be 0.9 centimeters. What's the precision? What's the uncertainty? And what measurement should she report? That's question number 2 that we did back there. A 1 kg object is weighed 4 times. We have 4 different readings. What's the degree of precision? What's the degree of accuracy? Okay? And what may cause the measurements to be inaccurate? So they're not really ask for precision and accuracy. What might cause them to be inaccurate? Shh, I'm recording. Let me do this one as this one here. To give you one more example, then you'll do B and C of this question, and these marks you'll automatically have then. 0.004 or 4 thousandths of a centimeter. So precise to the nearest 0.001 of a centimeter, and then your uncertainty plus or minus 0.0005 centimeters, just to clarify that. So that's your hand-in assignment, pages 33 to 37, 1 to 7, 27 marks. And I did a few of them just so that it's clearer for you. That will be everything. We'll shut this off.